Next is David Benjamin. David is an architect also, and heads The Living, which is recently become an Autodesk studio, but a very innovative firm. So we've talked about seeing reality, seeing buildings. We've talked about thinking about creatively, and David is exploring new ways of constructing and fabricating and growing and thinking about buildings. He is from New York, but did years ago live here in the Bay Area in San Francisco and was part of an indie rock band. So if he looks familiar, maybe that's why.
Thank you. So my architecture and design firm called The Living kind of explores the future of architecture, the future of the built environment, the future of buildings and cities through trying to prototype them today. And in our process of testing out new ideas and new technologies and new materials, we have been exploring a few somewhat unique ways to capture, compute, and create. And one of the ways I think about it is that maybe if you want to explore something new in terms of materials, in terms of the built environment, you know, some of the things that we've heard about already in this session and before this, then maybe you really have to engage in some way capturing and computing in order to create and test your idea. So I want to show two examples of what we have been up to. The first one is design with environmental information. And this is basically a project that involves capturing and computing a layer of data about the city and then creating a public interface to environmental quality. In other words, a cloud of light that hovers above the river and that changes color and blinks according to water quality, presence of fish, and human interest in the environment. More specifically, this works by putting a floating network of tubes out into the water, in this case, the East River in New York City. These tubes are about 6 feet long, half above water, half below water. Above water, we have a layer of dynamic LED lights, and below water, we have an array of sensors, and this is kind of the capturing element. The sensors, for the most part, are digital sensors for things like dissolved oxygen, a sonar sensor to detect fish, and basically the technologies of the Internet of Things, small embedded sensors in the environment and small microcontrollers to be able to process information and generate signals. The sensors, and this gives you a sense of our prototyping process, the sensors are detecting things about water quality, so the dissolved oxygen and other measures of water quality. They're also detecting the presence of fish, and they're detecting something that we think is interesting and relevant for the life of the city, which we're calling human interest. So in other words, they're detecting when people are interested in this important urban issue of water quality and environmental quality. And basically the way this works is we put this floating network of lights out in the river, and they register a few things about the environment and project it back to us. This is basically a way of creating a layer of light in the city that is in dialogue with the other lights that we have in the city. You see here our network in the foreground in blue with the dynamic LED light, and in the background the Empire State Building in New York City in green with a different kind of layer of light in the city. And this is partly to say that we think of our prototype here despite its small scale, as being a prototype for the building envelopes of the future. We're working on the surface of the water, but we see this as a kind of horizontal building envelope that is part of the visual skyline of the city. And we're thinking about ways that building facades can really come to life to communicate important information, and that we can use the building facade as a layer of information in the city. One of the aspects that we have added to this project recently is a layer of biological sensors. And this is a photograph of mussels, living mussels, the shellfish. And it turns out, here you see a tank of mussels, living mussels in a sped up fast motion. And you see this pulsing of the mussels because the mussels are opening and closing their shells. Well, it turns out that mussels open and close their shells at a rate and an amount that is a very sophisticated and sensitive detector of water quality. In fact, more sensitive than some of our best digital sensors. So in terms of capturing the environment, we're interested in using the technology of the Internet of Things, using physical sensors, but we're also interested in using biological sensors. And here we've created a kind of hybrid system where we glue an inexpensive Hall effect sensor to one side of a mussel's shell, glue a magnet to the other side, and that gives us the ability to register when the mussels are opening and closing their shells and how much. And combined with the digital layer in the city, this gives us a way of using a kind of a biological layer of information in the city. In other words, it gives us a way to combine, the age-old target of artificial intelligence as the best, that computers might have to offer, with something that's been around for millions of years, which we call natural intelligence or biological intelligence. And this hybrid system is something that we think is really interesting and is going to impact the way we think about designing the buildings and cities of the future. This project started out as a prototype, and now it's been commissioned by the City of New York to become a permanent 200-foot-long floating pier in the East River. You see the Manhattan Bridge in the background here in this rendering, and it's just steps from the Brooklyn Bridge as well. So it will be part of the kind of layer of information in the city, and all kind of made possible through this ecosystem of capturing information, computing things about it, and then creating it, bringing it to life. The second example I wanted to explore and describe here is about design with new materials and kind of life cycles, meaning the full life of material and of a building. And this project basically involves capturing and computing information about new materials, and then creating both a new brick, a new building block for architecture, and also in some ways a new paradigm or new way of thinking about sustainability. This video has sound. So this gives an overview of our original vision for the project, and then I'll describe kind of how we brought it to life through this workflow of capture, compute, and create. So this is a project for the Museum of Modern Art in New York City and MoMA PS1. It's for their annual competition to have a young architecture firm imagine a new idea for architecture and then build it over the summer in the courtyard of the museum. And basically our proposal started with thinking about a kind of possibilities for a new building material and a new way to think about life cycles of buildings. We were inspired by this loop shown here, which is the Earth's normal healthy carbon cycle. The cycle of endless looping of growth, decay, renewal, and regrowth that happens. And also our awareness that the way we make most of our built environment today is not very sustainable. In other words, we typically take high-value raw materials, spend a lot of energy converting those raw materials into building blocks, make a building, and then at the end of the useful life of that building, we put all of that physical stuff into a landfill. In fact, more than 30% of the landfills in this country are made up of construction waste. So this cycle that we do for most buildings is pretty unhealthy in terms of not only energy, but materials. And we were interested in this project in exploring the possibility of having a kind of new approach to this cycle. So in other words, we were interested in seeing if we could take low-value raw material instead of high-value raw material, spend almost no energy converting the raw material into building blocks, make a useful building, and at the end of the life of the building, literally biodegrade it, compost it, and return it back to soil and to the ecosystem. How could we possibly do something like this? Well, it turns out through this living organism called mycelium. This is a microscope video of the branching growth of the root-like structure of mushrooms called mycelium. And it turns out that you can take mycelium and combine it with agricultural waste. In this case, we're working with corn stalks, not the high-value part of corn, not the corn kernels, but the corn stalks, the chopped-up waste of agriculture, combining it with mycelium, putting it into a mold of almost any shape. And here you see in kind of fast motion, in 5 days, this solidifies into a solid object, potentially a solid, useful object that can be used for various parts of the built environment. In this project, we're working with a great startup company in upstate New York called Ecovative, and they had already been using this project for a variety of applications, including packaging material, and we proposed to collaborate with them to create a new type of building material, a new brick, that we could actually potentially build viable buildings out of. So this is the brick we designed. And since no one had ever built a building, a large-scale outdoor structure out of this new material, we had to do a lot of testing. So this is, in a way, our version of capturing for this project. We took our bricks, put them in a universal testing machine at Columbia University, subjected them to various forces. In this case, you saw a single brick being subjected to 100,000 pounds of crushing force. That's not a great result for a structural material to go, like you just saw, from 4 inches to about 1 inch when you get that much pressure. But it was very interesting for us to realize that this material actually exhibited some very unique properties and that they might, in fact, be interesting and valuable. We actually worked with structural engineers at Arup on this project. And the structural engineers thought that result of that brick being crushed so much, they thought that was fascinating, and that was great news. And that was good for me, because from my point of view, that seemed like it might be terrible news to have our brick be crushed that much. It turns out in our building, we only needed a single brick to withstand the force of 250 pounds. So that test of 100,000 pounds was just to learn about the limits of the material. 2 interesting facts structurally about the material that we learned through this capture process is that 1 brick can support the weight of about 50 cars. So that's pretty big. But also this material is 20,000 times less stiff than steel. The interesting point here, the takeaway, is that this material never quite fails. At least it doesn't fail catastrophically. It compresses a huge amount, but it doesn't crack, it doesn't explode, and even concrete and even some metals might experience problems at that amount of load. We did a lot of testing for this project, and we had to test not only the performance of a single brick, but what would an assembly of bricks perform like when we put them together with a natural compostable mortar. And here we're doing that test again at Columbia University. And the important thing here is that we had to do this testing in order to design, in order to compute and create. We had to do that capture because no one had used that material, and therefore in the structural engineering software there was no drop-down menu item for mushroom brick. So we couldn't tell how this structure would perform when we wanted to make a large-scale structure out of it. So here's the actual software we were using. This is proprietary ARP software, actually. A structural engineering software where we're inputting, using the capture data to input the material qualities that we need to compute the structural forces and the behavior of our structure. I won't go into the details of our iterations and our design, but I'll just say that when we first simulated the first design of a brick, the first design of a macro structure, this 40-foot structure, we had a huge problem under hurricane force winds. The red area is displacement of more than 30 inches. But after several rounds of changing this organic living system, iterating on the ingredients and the growing conditions of a living organism, changing the shape of the brick, slightly changing the macro shape of the structure, we were able to get within loads and performances that we thought would make a viable structure. Another important thing to note about the material that we kind of captured was that it has a very different property on the exterior than on the interior of these bricks. And that means that you can't cut these bricks on site to make complex geometry. And this led us into a kind of separate iterative workflow in terms of design and computing. We were computing and designing different shapes of bricks, and then when we found a brick that we liked, we were able to determine that this type of brick would work well if we were stacking it to create a straight wall. It would work pretty well if we were creating a singly curved wall, but as soon as we created complex geometry with a doubly curved wall, then we had to change the rules. Either the bricks wouldn't add up to the right course length, or if we distributed the leftover space, then we would get problems where the bricks wouldn't properly stack on one another. We went through a lot of different ways to try to compute a system for stacking these bricks, 10,000 bricks into a 40-foot structure that would be viable. And we ended up creating a system where we inserted a filler brick of a half module, a filler brick also of a quarter module, laying those out so that each course was the right length, but also going through and checking every single brick out of 10,000 to make sure it lined up properly on 2 bricks below it. And that was the compute part of the process that we did in a way that would never have been possible by hand or by a simple rule of thumb. We really needed the iterative process of the computer to do that. And here you see the 10,000 bricks laid out. The blue are the half bricks, the red are the quarter bricks. And finally, this allowed us to do something that was one of the final challenges of the project, which was to build the structure within about 3 weeks on site. We hadn't resolved quite all of the issues by the time we got there. And one of the things that was interesting in this final part of bringing this project to life was basically solving problems on site with 2 completely different kinds of expertise. One was Columbia Master of Architecture students who have great experience with computation and with complex geometry. And the other is New York City brick masons who have great experience with how to put together solid structures with bricks. Neither one alone knew how to solve everything about this new type of project, but together they were able to collaborate and make this thing work. I'll just show a final few images of the project. This shows the building in its completed form in the context of the glass and steel buildings of Manhattan in the background and the brick buildings of Queens in the foreground. So it's this kind of dialogue of building materials with other building materials, forms with other forms. Here you see the way the structure kind of interacts with the natural environment and frames the sky. It was important for us to test the kind of creative capacity of the material as well as the technical capacity. So we're very interested in the performance of light and shadow, texture and pattern, what it was like to stand inside a huge amount of this new material, something that's very difficult to capture or compute. So we really needed to build it to test this out. And finally, perhaps the ultimate test of this project every year is its ability to host parties, because every Saturday during the summer, 5,000 people come to the courtyard of MoMA PS1 to hear experimental electronic music. And in a way, this was the kind of fitting finale for the project, which was to be tested out in the public, out in culture and society, not simply within a laboratory or on a vacant lot somewhere, the way a lot of facade mock-ups are tested. The project took on a life of its own, and a kind of debate and discussion through social media in pictures like this and very short comments, which was interesting for us to follow as we're testing out the viability of this material and the idea. We created a second alternate version with different forms and textures. This is a compostable dye that makes the reddish color. And finally, the takeaway message for us was that it may be possible to design buildings to disappear as much as we design them to appear. In other words, to think of that full life cycle of the materials, the energy of the building, and where all of this physical stuff goes at the end of the life of the building. And here's our kind of diagram of going from crops to construction to compost and back to crops, all within a single project, creating this healthy life cycle, made possible through this rough workflow of capture, compute, and create. Thank you.